All right. Yeah, so I've collected the stuff. The odds are on the left. Yep. Anyone else have that? Okay, any questions over homework at all? 25? 25x plus x to the negative 1. That one? 25 or 26? Okay, so let's look at this one. They gave you h of x was x plus x to the negative 1 cubed. Well, the only way to use the power rule, which is what we learned last time, is to be able to expand this out because you've got this cubed up here. So I have to multiply this out. That means it's, that times itself 3 times, right? Now you have a couple options here. I could use Pascal's triangle. Remember how I had that? We said x plus h to the 0, x plus h to the first. Remember this? X plus h squared, x plus h cubed. And when you do that one, you got x cubed plus 3x squared h plus 3xh squared plus what? H cubed. That's what you would get if we were trying to expand x plus h. But here for us, what's h? X to the negative 1. So if I replace all the h's with x's to the negative 1, I would get the same result. Okay, so let me try that. I'm going to rewrite this. I'm not taking derivative yet. H of x equals x cubed plus 3x squared h, but we said h was x to negative 1, plus 3x h squared, which would be x to the negative 1, but then squared, right? Are you following what I'm doing here? Or are you all completely lost? Yeah. Let me do one more and I'll explain here. Hold on. X minus 1 cubed. I'm replacing all the h's with x minus 1. I'm using the binomial expansion to just make it easier than actually having to multiply it out by hand. Now this becomes x cubed plus, what's x squared times x to the negative 1? What do you do to these exponents? Or add. 2 take away 1, right? So 2 take away 1 would be 1. So that's just 3x plus, let's see. Here, if I have something to a power and then to another power, I multiply. So that's negative 2, yes? This one is x to the 1. So what's x to the 1 times x to the negative 2? X to the negative 1? Again, subtracting, right? 1 take away 2. And then the last one, x to the negative 1 cubed would be x to the negative 3. And now I have 1, 2, 3, 4 terms, and I can do derivative of each one with the power rule. So the derivative is 3x squared plus 3 minus 3x to the negative 2 minus 3x to the negative 4. Now that may not be what the back of the book had. It does? That's what it has? Okay. Do you understand? Yes. Where's that? On which one? Right here? Okay, so this right here is x times x to the negative 2, right? Because this piece right there is that. This is a negative, that's a positive 1 there. And I'm using the property x to the n times x to the m is x to the n plus m. You add the exponents. So if I take 1 and add negative 2, it's the same as subtracting 2 from 1, so I get negative 1. Is that okay? Were you wanting to multiply it? Is that? That's correct. That gives you this. But then when you put these two together, you don't multiply the exponents, you add them. Yeah. You have to remember the difference between these two formulas. If you have two bases, different exponents, you add the exponents. If you have one base to a power, you multiply the powers. Okay, the other one you said 23 and 26, both? Number 23 was z equals capital A over y to the 10th plus b cosine y. All right, first thing I'll point out is that A and B here are just constants. They're not our variables, all right? So we're just going to carry them like they were numbers the whole time. The other thing to point out is that y is our variable. All right, y is the variable. Now, how do we know that? In the beginning of this book, the author talks a little bit about, throughout the book, when you see x, y, z, those are always variables. When we use alpha, beta, when we use A, B, C, D, those are always going to be numbers. I'm just telling you that now, all right? That's how we know that. So I'm going to use power rule, but I cannot use the power rule on y to the 10th until I do what first? Bring it up, right? Bring it to the top. So this is going to be, the A stays there, y to the negative 10 plus b cosine y. Now I have two terms, right? Addition between them. So when we take derivative of two terms, we just do derivative of each one. So z prime is equal to, now what happens when we have constants in front of a function? They just come down, just comes with it, right? If it's constant by itself, the derivative is 0, but that a is not by itself. So a is here. Now, what's the derivative of y to the 10th? Negative 10, y to the negative 11. And that's it. That's the derivative of this first part. Then we say plus. Again, the b, nothing happens. And then we talk about what this was? Negative sign, right? Negative sign. So negative sign y. Like that. So a final answer would look like this. Negative 10a over y to the 11th. You could leave it up as negative 11. That's okay. And then over here, I'm going to pull that negative out and make it minus b sine y. That answer that question? Yes? 24? Yeah, I'll do 24. And but 26 also, right? Someone asked for 26 or no? Yes? All right, let me do 26 and I'll do 24. 26, u was equal to, I'm doing the other one. I'll come back to that. What the hell is that? Cube root of t squared? Yep. Plus 2 square root of t cubed. So I'll just remind you of this. Back, I don't know when it would have been, you were introduced to radical notation and how to convert radical notation into rational exponents. And this is the formula for it. When you have the mth root of x to the n, then that can be converted into x to the n over m. So whatever the root is goes in the denominator, whatever the power is goes up here. Does that make sense? How do we rewrite the square root of x? Is x to what power? 1/2. Why is that true? Well, it's the square root, right? And x to the first power. That 1 goes here and that 2 goes here. It's that formula is what we're using. Okay? All right, so rewriting this first, because I can't take derivative till I get the powers written as rational numbers. So this is t to what power? 2/3 plus 2t to the what? 1/3. No? 3/2. Good. I confused myself there for a second. It's like, what the hell? Because if there's not a root out, if there's not anything out here, what is it? A 2. So that's why it's 3/2. If there is a number out here, then you have to write that number. And now we just apply power rule. So my derivative, u prime, the 2/3 comes out, right? T to the, now I have to take 2/3. If you did your homework, do you feel a little more comfortable with fractions now? Okay, all right. 2/3 take away 1 should be negative 1/3. Plus, now the 2's out there, right? But the 3/2 hits it. 2 times 3/2 is 3. 2's cancel. So you get 3 t to the 3/2 take away 1, 1/2. Now I could rewrite this as 2/3, and then if I wanted to, could I put that to a root again? What root? Cube root. And then over here I could put 3 square root of t. I'm not sure what the back of the book would. Well, this was an even problem, but I know there's even solutions running out. You know, they run. You can get even solutions somewhere on the web, right? Sure, they're out there somewhere. So the book either has this or this. All right, and then finally 24. Y is equal to sine theta over 2 and then plus c over theta. C here would be a constant, wouldn't it? The variable in this problem is theta. So theta is like the x. What I like to do is I like to rewrite that 2 on the bottom like this. Now, do you agree with this? Theta over 2 is the same as half of theta. And then over here, bring the theta up and theta to the negative 1. If you do it that way, then you have a constant, right, in front of sine. So the constant stays there. Derivative of sine is cosine. So you should have 1/2 cosine theta. And then this is a constant, so it's going to stay. Negative 1 comes down and becomes negative c, so I'm going to go minus c, theta to the negative 2. And now you could drop that theta down underneath the c if you wanted to and make it like a theta squared underneath, and you're done. Yes? If you're saying that I don't take it personally. Let me ask you, what's your major? I would suggest you just get used to it, because the problem is that later on you're going to have problems that involve x, theta, u, v, and they're all going to be in the problem at the same time. So if you don't like the thetas, you can't switch them to x's because you already have x's in the problem. You know what I'm saying? So you just kind of, I understand, because I remember when I was a student, it's like all these other symbols, just, if I understood it for x, I understood it for everything else, right? However, you just want to get comfortable with it. You don't want to like see thetas and be like, oh, and you know, freak out and not know what to do. Yeah, you know. So I don't mind if that's what it is in there. That's fine. All right. I think we're ready to move on. I'm making that decision for us, I guess. All right, so we are getting through chapter 2 here. Oh, no, we didn't finish 2.1, did we? No, we did not. There was one thing I want to talk about. We had started class last time with the problem. Remember this? All objects on Earth, blah, 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 right? Yes? So I asked, well, if every object on Earth falls at the same rate, then what's the velocity of every object on Earth at a given point in time? And then what's its acceleration, right? Did we do it? Now I'm thinking about it, we did. When did I do it? Very end? Huh. Oh, I gave you a specific example. That's what it was. Okay, so I do want to talk about it because I wanted to give you the general formula for it. All right, so we said last class that on Earth, with no air, that wouldn't be a very fun place, that we have d of t equals negative 16 t squared plus v naught t plus d naught, right? No. But if you take physics, you'll see it again, so you may, get comfortable with it, I guess. So if that gives me the position of an object at every point in time, and I now want the velocity at every point in time, I just need to take the derivative of that. Now, the variable here is what? T, because it's d of t. What's v naught? It's a constant. I don't know what it is, and d naught is something I don't know either. But so I'll just treat them as constants. Of course, negative 16 is a constant. So the derivative of this is what? Negative 32 t plus v naught times the derivative of t. Derivative of t is 1. And then derivative of d naught is 0, because d naught by itself is a constant. So derivative of constant is 0. So on Earth, if you drop an object, its velocity, its speed at a given point in time is negative 32 times t, the amount of time it's been falling, plus the initial speed. Now the initial speed, remember, I said you could just let it go, you could throw it up, or you could throw it down, right? Now this is measured, just because I did give you units last time, this would be measured in feet per second. Feet per second, yes. Initial, so that naught is like a 0. So it's saying the velocity at 0 time, or initial or starting velocity. It's used in physics all the time. They use the little naught symbol for starting times and things. Starting conditions, initial conditions is what they call them. All right, so that's our velocity. We can get acceleration by taking derivative of that, right? And the acceleration in this case would just be what? Negative 32. And this would be measured in feet per second, which is feet per second squared is sometimes how you see it. And I said that was actually the acceleration of gravity, right? Why is it negative? We're going down. We look at even the velocity. When we talk about velocity, when we drop objects, we have to decide what up is and what down is. And we consider up to be positive velocity and down to be negative velocity, right? It's kind of like, if I take my soda here and I throw it at you, right? It's moving away from me, but it's moving closer to you. So is it moving positive away from me, or would you consider that negative? So we have to orient ourselves. We just say up's positive, down's negative. That's the way we do it. You could say up's negative and down's positive. That's fine, as long as we all agree, and that's what we do, and that's what we do. All right. Now, let's just try a quick problem, see how we could apply this. Example. Let's say we have d of t equals negative 16 t squared plus 1200. And that's it. could you look at that as being an object being dropped on Earth? Does that follow into the format of an object being dropped on Earth with no air? Yep, you've got negative 16t squared. Do you have V naught t? Kind of. What's V naught? It's 0, right? Because there's no t term here. And then you have D naught. What's D naught? 1200. So this is really an object being dropped from how high? 1200 feet. Okay? We're going to let it go. Here's the question. There's a couple of questions. How long till it hits ground? B, what is velocity upon impact? So it's going to take a certain amount of time for this object to hit the ground, right? And when it hits the ground, it's going to have a certain speed. I'd like to know those two things. How long does it take to hit the ground? And when it gets there, how fast is it traveling? Agreed? Or, I mean, not understand what I'm asking? Okay, so how about answering the first question? Okay, solve what for t? We do need to solve for t because it's saying how long, right? Time? So we do need to solve for t, but what are we solving? Because that's not an equation, that's a function, right? What does that function tell you again? That's what this tells you? Like if I plug in a time, what does it spit out? An answer, right? What is that answer? What does it represent? How far off the ground it is. So like at time 0, right? If I plug 0 in here, how high am I? 1,200 feet, right? Then as time goes on, 1 second later, right? 1 second later, plug 1 in here, take 16, subtract it from here, I'll be what? 1,984 feet off the ground still, right? 1 second later. Then 2 seconds later, I'm at a different height. I'd like to know how long it takes to hit the ground. So what do I have to figure out? I want to know when this is what? 0, right? That's the equation you need to solve. You need to figure out when negative 16t squared plus 1,200 equals 0, right? When that will give me the time it took to zero this thing out, right? And 0 means I'm on the ground. So just solve this. You can move the 1,200. You'll need a calculator. Or I'll need someone in here to get a calculator for me. Somebody take the 1,200 to the other side. Divide negative 1,200 by negative 16. Exactly. And now finally, to figure out what t is, you take the square root on both sides. Hold on. It's what? I'll take 8.66. Approximately. And that should have been plus or minus, right? But why don't I care about the minus answer? Yeah, we're not talking negative time, right? Time is positive, so we're just going to say about 8.66 seconds for it to hit the ground. With me? All right. Now, if I know how long it takes to hit the ground, I should be able to figure out its speed. We just talked about the speed. The speed is the first derivative of this. What's the derivative of this thing? Negative 32t plus nothing. That's it, right? Negative 32t. So now that I know how long it took, right, I can just plug it in here, say, well, what's the velocity at 8.66 seconds? And you get, what, negative 32 times 8.66 is approximately what? 277? I'll just say negative 277. And this would be feet per second. 277 feet. is almost a football field in 1 second is the speed at that instant in time. Right when you hit the ground, right when that thing hits, right, 1,200 feet, right when it hits the ground, it's traveling at this speed. Now, a lot of us don't have a good idea of how fast that is. We all know what 50 miles an hour feels like, right? Right? The difference between 5 miles an hour and 50 miles an hour, we all understand? Okay. So I'm going to convert this to miles per hour to give you an idea what the speed is, just as an exercise in what's called dimensional analysis. It's just changing units. Negative 277 feet per second means 1 second, right? You all right with this? I would like to convert this to miles per hour. So to do that, I need to convert my feet to miles and my seconds to hours. So you have to know the relationship between how many feet there are in a mile. And that's just something you either know or don't know. And if you don't know, you've got Google, right? So how many feet are there in a mile? 5,280. So I want the feet to go away, right? So I put the feet down here so that it's on the opposite of where the feet are up here. So I put feet down here, and then above it I put miles. I'll just put M for miles. Is that all right? I know that 1 foot is 5,280 feet. Okay? Is that all right? Now, seconds. I need to go from seconds to hours. How many seconds are there in an hour? 3,600. There's 30 seconds. There's 60 seconds in a minute and 60 minutes in an hour. So it's 60 times 60 is 3,600. So 3,600 seconds in 1 hour. Notice I put the seconds on top. Why? To cancel the seconds on the bottom. So I'm going to cancel my units. Feet cancel, seconds cancel. All I'm left with is miles per hour. So my answer is going to be in miles per hour, which we like to write, what, MPH? MPH is the same as miles per hour. That's the same. Now, to actually compute it, you need to go straight across the top. Multiply negative 277 times 1, you don't need it, times 3,600. So someone do that in a calculator. And then divide it by what? 5280? 188 point what? 86? Close enough, approximately. So what do you say about that? It's moving, isn't it? It's moving. Now that's if there was no air. For those of you who know anything about, jumping out of airplanes or anything like that with parachutes or something, there's something called terminal velocity, which is the fastest that you can possibly go. I mean, it gets to the point like you jump out of an airplane with a parachute, right? The parachute slows you down to a certain speed and then you can land safely. Well, if you jump out without a parachute, you keep speeding up, but you get to a point where your body is the parachute and you get to a maximum speed and you just can't go any faster than that. And I believe the maximum speed is like 130 miles an hour if you have the atmosphere. If there's air there, then there's like a terminal velocity. Is that, okay. Now, the reason why I do this example is because I've always found this example. I do the same example in college algebra, except I just tell them what the velocity function is. I don't show them where it came from. Because the reason I always did this was because right after 9/11, we were teaching out of a math book that gave an example of dropping a penny off the World Trade Center. And it was after 9/11, so there was no more World Trade Center, but the book was, we were still using it. And so when I got to that problem, I was like, whoa, hold on, that's kind of morbid to be talking about this, right? So instead, the class, we looked at it as, that day people had to make decisions, right? I mean, some people made this decision that day instead of burning alive, 1,200 feet, right? Now, they all reached terminal velocity, but it was still moving. But instead of thinking about people jumping off the building, which is kind of sad, let's think about something else. If you go back, I know September 11th was just a couple of weeks ago, right? So I don't think anyone could turn on the TV without seeing the buildings coming down again. I mean, they show it every year at that time, right? So if you have ever watched it, it almost looks like it's slow motion, doesn't it? It almost looks like slow motion the way the building falls. If you time it, it's about the building was about 1,200 feet high. Okay, it takes a little bit longer than 8 seconds to actually fall. But what's amazing about it is if you were to drop an object, here's the World Trade Center, and here's an object. If you were to drop an object in the World Trade Center, they both fall. You would think that this object would get to the ground much faster, right? Because this one has to not only fall, but it has to do what? It has to basically crush everything there, right? Everything there has to be destroyed as it goes down. That's how much energy there was there. The fact that it still took this almost the same amount of time as it took for something to fall free fall, the fact that it still took just about that same amount of time meant that the actual destruction of its own frame and concrete didn't really slow down the actual process of getting to the ground. I don't know. That's always boggled my mind, the amount of energy released in that collapse. It's just, I don't know if you've ever worked on a car and just tried to like jack up a car, or ever had a big piece of metal and had to move and just, God dang, man, this is the beams in that building were just massive concrete that was turned into dust. I mean, that's energy that you can't even fathom, that sort of energy. Anyway, it always blows my mind. So this is a formula that basically we've tied math to the real world. We dropped objects. We've tried to figure out, what's going on here. We figured out that a quadratic function was a perfect representation of what's happening when you drop things. And then you could tie it to anything you drop. I remember I had I have 2 cats. Did I tell you about my cats yet? It's a long story. I don't like cats, but my best friend's wife was a cat lover, and I took these cats. So they're outdoor cats. I still have them, but one of them, I was going outside, and I spooked her, and she jumped off the balcony. Like, if you go outside the back of my house, it drops off 16 feet, and so it's like a deck that goes out, and I like spooked her, and she just jumped off. And so she fell and she lived, and I was like, damn. So I computed her velocity at impact, right? Because I knew, what her height was, and I knew how long, then I could figure out how long it took her to get there. And then I was like, damn, she hit like at 30-something miles an hour, and she lived. Wow, that's pretty good. Cats are tough, I guess. But so you can do it for anything, All right, now, we're going to get on to today's stuff, all right? I've already killed almost 40 minutes of class. I apologize. Do you remember this? If you have a parabola, f of x equals ax squared plus bx plus c, that all parabolas either open up or down, right? They go up or they go down, or they can go sideways, but let's just stick with functions, vertical line test ones. Okay, we have this point called a vertex, right? And there were 2 ways in college algebra to find the vertex. You either completed the square, which was not fun. Well, it was fun, but you don't have to admit that. And then there was another thing. It was a formula. Do you remember there was a formula? It said, yeah, it was a vertex formula. It was HK. It said H was going to be negative B over 2A. Does that look familiar? Show of hands. How many of you remember? Okay. Because if enough people do, then I'll keep going. If no one knows what I'm talking about, then there's no sense. And then to get K, all you did was you plugged whatever you got in here back into the function that gave you the K. Well, when I'm in college algebra, I always tell my students what we have to do is we have to thank Isaac Newton and calculus for this formula, because I don't like to push the completing of the square as much because of this formula. But here's where it comes from, all right? Let's think about this for a second. If we have a parabola that opens this way, or I'll just draw another one over here so we can, ooh, that doesn't look like a parabola. Either of these cases, do you agree that the slope of the tangent line at that blue dot is 0? Right? The slope of the tangent line is 0 here. Slope of the tangent line here is 0. That means the derivative is 0 there, right? Yes? So what I'd like for you to do is I'd like for you to take the derivative of this right now. What's the derivative? It's 2ax plus what? B plus nothing, right? So we're doing the a is a constant, 2 comes out, power comes down, b is a constant, bring it, derivative of x is 1, derivative of c is 0, right? Now we said that's the derivative, and I know that this point is going to be when that derivative is 0, right? So set this thing equal to 0. And what do you get? Solving for x. Move the b over and divide both sides by what? 2a. And you get x must be what? Negative b over 2a. So it's saying the x-coordinate of that highest point, which we call h, must always be negative b over 2a. That's all it is. It's just one simple application of that idea. What we're going to do in this class is what we couldn't do in college algebra. If in college algebra we got to a nice polynomial function like this, we didn't have a formula for finding these highest and lowest points. And I've already alluded to this in this class. So what we're going to do is we're going to go figure out when the derivative is 0, right? Because that's going to give us highest and lowest points, right? All right. All right, this is where we ended class last time. Right? Said you should know these first 3 and know that these exist, these other ones. And those are all on your formula sheets. All right, we have two more sections that involve taking derivatives and these new rules. 2.4 is there's 2 rules in this section. We call it the product and quotient rule. Then after this, next week, we'll talk about the chain rule. Chain rule by far is the most important one, and it's the most difficult one. But like anything else, you have to get these down before we can get to that one. So right now, up to this point, that's it. Those are the notes for that section, right? That's all. That's it. It's just those 2 formulas. That's it. So I will talk about these in some different notations I'll be using. But here's the basic idea. If I have y equals x sine x, right now we really don't have a way of handling this. I've never given you a problem like this intentionally because you couldn't do it. Because what we have is multiplication between these 2. If it was addition, couldn't you just do each one separately? And you just add the 2 answers? If it's multiplication, though, you may want to do this. Don't write this down. You may want to just say, okay, take the derivative of x and get 1 times the derivative of sine x, which is cosine x, right? And let me tell you something about this. If it were that easy, Calculus 1 would not be as hard as it is, and Calculus 2 would not be as hard as it is. The problem is it's not that. Okay? If you do that on the test, that shows like complete misunderstanding of the way things happen with this. All right? When you have a product, right? This is a product, multiplication. We don't show the dot, but when we have a product, we must apply the product rule. The product rule. And the product rule says this. Here's a notation that I'm going to use. If I have something, I'll call it U, times something else, which I will call V. So I just have 2 things, and they're being multiplied together. U could be x here, right? And V could be what? Sine x, right? All right, if you are going to take the derivative of that, it is not just U prime times V prime. It is U prime times V, but not the derivative of V, just V. Then plus V prime times the derivative of U. V prime times just U. That is the product rule. Here's some other ways you may see it. You may see if I have f times g, and I want to take the derivative, it will be what? The derivative of f times the g plus the derivative of the g times the f. Now, you're going to hear me talk through the product rule a lot today and through the rest of the semester. Even in Cal 3 today, I kept on saying the product rule thing. The product rule is always going to have two things being multiplied, a first function and a second function, right? A first and a second. The product rule is the derivative of the first times the second plus the derivative of the second times the first. However you get it into your head, you need to get that like just completely nailed down, all right? Derivative of the first one times the second one plus derivative of the second one times the first. You think you can memorize that? All right, so for this one, the derivative here would be, and I'm going to go through some steps here. I'm going to go up here, I'm going to label these. How about we call that x? Right? That's like the x is my u and the sine x is my v. Yeah? So what I'm going to want to do here is have the derivative of x times the sine x plus the derivative of the sine x times the x. Do y'all see how I'm using the prime marks here? This is my product rule. Derivative of the first times the second plus the derivative of the second times the first. What is the derivative of x? 1. So y prime is 1 times sine x plus, now what's the derivative of sine x? Cosine x times x. Now I'm going to write this down one more time, getting rid of that 1 and just writing sine x. And this is just a notation thing. This is dangerous notation right here, because someone might think that what you mean is to put x together there and square them, right? You might, maybe. So what we do, because that x is actually trapped in the cosine and that x is outside, is we slide the x in front of the cosine so that there's no confusion, no mistaking, it's multiplication. Box it up and you're done. Yeah? You like that? What's that? You're good with this? Well, what becomes challenging is when you have to put all the rules together and you have a complicated function that involves multiple rules. That's where things can get a little bit little nasty. All right, well, let's try something else. Well, that's what I wanted to ask you. All right. Do you see a product? Right there? Okay, now, thank you. Before I actually go and try and do the product rule, does everyone understand we could multiply this out and do power rule, but we can't do power rule now, right? The reason we can't do power rule is because it's this times this. If it were just this, of course you could do the power rule. But you would have to multiply, so I'd have to go x to the 4th times x to the 7th, x to the 4th, and do all that and expand. That would be a mess, wouldn't it? That's why the product rule is going to be great, because we're just going to be able to apply the rule and we'll be done. We have two things being multiplied, right? I have this thing u, and I have this thing v. Now, they're big things, right? U is a big thing, v is a big thing, but I can take the derivative of them individually, can't I? And that's all I need for the product rule. So the derivative will be, now did y'all like how I wrote u with the prime mark first and then the v and then the plus? Or do you want me to do the derivative now? Write it first? Write it first? Okay. So I'm taking x to the 4th plus 5x cubed plus 3x squared minus 7x minus 4. That's my u. That's my first function. I'm going to take derivative of that times the other one, right? Am I going to take derivative of this one? Not yet. Then what? Add to that. I'm going to run out of room, so I'm going to have to go on the line below this. It's going to be plus the x to the 7th minus 4x to the 5th plus 7x squared minus 10x plus 1. That one derivative, right? Then times what? The first one, right? Which was x to the 4th plus 5x cubed plus 3x squared minus 7x minus 4. You don't have to write this step, all right? You could, if you wanted to, just go straight to like taking that derivative and putting it there. Should I highlight the fact that these are the derivatives right there? Yeah. All right, so our answer will be, what's the derivative of that first parentheses there? 4x cubed, 15x squared, plus 6x, minus 7. And that's it, right? Then times x to the 7th minus 4x to the 5th plus 7x squared minus 10x plus 1 plus, now I need the derivative of this, which is 7x to the 6th, 20x to the 4th, 14x minus 10 times, what's that? 14, yeah, thank you. I forgot my x on my 14. Times x to the 4th plus 5x cubed plus 3x squared minus 7x minus 4. And that's it. We're done with the derivative. I call this the raw derivative. I mean, this is it. We applied the rule. That's the derivative. Now, it may require some cleaning up, which wouldn't be fun, but you see how the rule was applied, though, right? Another example? This is y. Y equals this. I want us to find the derivative. So when you look at this, is it obvious that there is a product? Yes? All right, so this is my u and this is my v then, if that's what I'm going to do. Now, if you're going to do this, that means you need to be able to take the derivative of u and v. Like, you need to be able to handle those. Can you take the derivative of u? Not like that. What are you going to have to do to it? Break it up into what? 3 different fractions, right? And then you can go after it. So maybe it might be worth it to go ahead and break it up now before I do anything else. The first one will become 1 over x, right? 1 over x, which is the same as x to the negative 1. The next one is x over x, which is 1, so plus 1. And the last one is negative, let's see, x squared over x, which is negative x. All of this to the, I'm sorry, all of this times this. And notice that 1 over x over there, I got that and multiplied, or changed that one. We okay with this? Could we multiply this out and use power rule? Yes, you could. But as we'll see in a little while, you won't want to do that. You know, it's too much work. Okay, there's my u and my v. Here we go. You know what I'll do? This time I'm not going to write it with the prime. What I'm going to do is I'm doing it in red, the part that I'm taking the derivative of. So I'm doing what? U prime first? So what's the derivative of u prime, or derivative of u? Negative x to the negative 2 plus 0 minus 1. So derivative of this is this. Derivative of 1 is 0. Derivative of negative x is negative 1. Now that's times what? Times v, right? Don't change it. Plus now a derivative, right? But it's the derivative of this one. So 2x plus 3 what? Minus x to the negative 2, right? Done? Times, right? We're not done. That's the thing I see people be like, I got the derivative, and they forget, like, there's a product rule going on here. You have to throw that last piece on. So times what? X to the negative 1 plus 1 minus x. Is that okay? The red ones are the derivatives. Derivative of the first times the second plus the derivative of the second times the first. F prime g plus g prime f. I didn't. Why didn't I? You need to get glasses, man. Get those fixed. No, it wasn't there. Thank you. Y prime, right? That's our derivative. Now, again, we could multiply this out and clean it up and everything else, but the derivative part of the problem is over. Is there a question? If I ask you for just the derivative and I, don't say simplify, like on a quiz that I might give in class next week, walk in, where I think it's time for us to do something like that, have a quiz, I would just ask you for the derivative. And that way, it doesn't take a whole bunch of time. You just crank out the derivative real quick. So that would be your final answer. You'd box it. Now, okay, how about this? That's for you. Using the thetas instead of the x's. I want us to find the derivative of w. Okay, derivative of w. And I'd like us to find the derivative of w. Theta is our variable. Can we apply the product rule? Yes? Because we have a product right here. Sometimes you'll see me do this. I'll put like a dash line in between them so you can really kind of see where the product is occurring. And then I call one of them U and the other one V. The derivative of W will be U prime V plus V prime U, right? Do you know what the derivative of U is? Cosine theta times tangent theta plus derivative tangent theta is secant squared theta times sine theta. There's your product rule. And I'll just put it here. This was U prime V plus V prime U. All right. That's it. We'll end it early today. Thanks for coming. Y'all have a good weekend. I'm just kidding. I'm just messing with her. Everyone's all excited. Really? I thought y'all were having fun. I thought you were enjoying yourself. You want to leave? I'm disappointed. That would have sucked, right? You come in and I let everyone go? Oh, you came to. All right. Well, you missed a lot of fun. I mean, we've had a good time so far. Okay. We'll turn it in. Yeah. Can I get that? Right. We've heard that. We've heard that before. Thank you. It's okay. It's okay. No worries. This is an okay answer, right? I mean, like it's okay. I mean, we're done, raw derivative. But, I mean, there are some things that we could do here. Like, maybe we would realize that tangent is sine over cosine, right? And wouldn't that cancel with that cosine? So that's really just a sine. Yes? I'm going to do it because when you start seeing these answers in the back of the book, you're like, what the heck, man? What'd they do? Tangent is sine theta over cosine theta. Plus over here, secant is 1 over cosine squared, isn't it? Of course it is. And then this is sine theta over here. Y'all agree all I've done is rewritten the problem? I said the cosines will cancel, which leaves me with just sine theta. And then plus, if I had sine over cosine, it would be tangent, wouldn't it? I could peel one of those cosines and put it here, couldn't I? And make that a tangent, but then what would the 1 over cosine in front of it be? 1 over cosine secant. I'm just showing you that's another way I could have written the problem, the answer. This wouldn't be wrong, but this wouldn't be wrong either. Now look, I'm going to give you now the quotient rule. All right? The quotient rule? Y'all ready for quotient? At least you're honest. So what if I said this? Y is equal to x over sine x instead. And you know what? Let's make it even better. Let's make it sine x plus x squared. There we go. That way you can't try and pop that sign up and make it a cosecant and try and get the product rule going. I'm forcing you to use quotient rule. Can you split this into 2 separate pieces? If we have 2 terms on the bottom, 1 on top, you can't. If it were the other way around, you could do it, but you can't. All right, do you see we have a quotient, though? Quotient meaning division. So instead of having u times v, I now have u divided by v. And that brings us to the quotient rule. Now, again, life would be great. Don't write this down. Okay? Life would be great if the answer was just this, right? What did I do? Took the derivative of the top, took the derivative of the bottom, and I'm done. I walk away and I get an F in the class. That, you know what I'm saying? That's not the way calculus works. Unfortunately, it just does not work out that way. Now, I haven't proven the product rule and quotient rule to you because the proofs might make you ill if you see them. But if you want to see it, I can show you. Come to my office and I'll show you. If you really want to see where the quotient rule or product rule comes from, it's really kind of cool. But I think my definition of cool and your definition of cool might be different things. So, so what do we do in this case? Well, I have good news, all right? For the quotient rule, here's the actual rule. Here's what we're going to use. I have u this time divided by v instead, and I want to take its derivative, right? It will be, check this out, you're going to love it, u prime v minus v prime u. What does that look like? That looks like the product rule, except a minus, right? But divided by v squared without a derivative on that v. So it's the product rule we had before with a minus instead of a plus. But then you have to divide the whole thing by the denominator, whatever it was, squared without taking its derivative. So do you all see you're just going to have to apply the product rule, but make it minus instead, and then just tack this thing on underneath it? Yes? All right, so let's do this problem here. The top here I'm going to call the top u, and I'm going to call the bottom down here v, right? Can you take the derivative of u by itself? Sure. Can you take the derivative of v? Well, it's two pieces. With addition, can you do the derivative of each one? Yes, so we should be able to handle this. So y prime will be, I'll do the prime marks for you this time. It'll be the derivative of the top times the bottom minus, instead of plus, the derivative of the bottom times the top all over the bottom, the entire quantity, whatever it is, squared. So I had those little prime marks on there, right, this time? I probably won't do it after this one, but what's the derivative of x? 1 times that thing, right? It's 1 times this whole thing, which is just itself, right? Sine x plus x squared. Now be careful here because we have subtraction. Subtraction is always tricky. What's the derivative of this? Cosine x plus 2x. And I need to put that in parentheses because it's two terms. And that's going to be multiplied times x at the end here. Then all of this over that whole thing squared. And we rarely actually square this out. We rarely do. We usually just try and clean the numerator up if possible and just let it be. I think the numerator does clean up a little bit. Well, no. Well, do you see how it would clean up? If this x goes through here, this would be x cosine x, right? This x goes right here, become 2x squared. And I have an x squared here, so I could combine those together. And that's about all I could do. So I will take it further. Sine x plus x squared. Minus, I'll distribute the x through first. Now to drop the parentheses, I have to pass that thing through, right? The negative? Any questions where I got anything there on the top? Bless you. Again. You see what I'm saying? I can put these two together. X squared minus 2x squared is minus x squared. And that would be about as much as I'd want to do with that. Sine x minus x cosine x minus x squared over all that stuff squared. What do you think? That's it. That's the end. What's the derivative of this? Secant squared x? Okay, let me show you why. All right? Check this out. Do you agree that this is sine x over cosine x? Now you have a quotient, don't you? We can apply the quotient rule to this quotient. We call the top u and the bottom v, right? Okay, according to the quotient rule, the derivative of this will be the derivative of u, right, which is cosine x, times v, which is cosine x, minus the derivative of v. What's the derivative of cosine x? Negative sine x, times u, which is sine x, all over the bottom squared, so cosine x squared. What happens when I put this minus and minus together? It becomes plus, right? What's cosine squared x plus sine squared x? 1. That's from pre-cal. Remember that identity? Cosine squared x plus sine squared x would be 1. You look it up on your formula sheet if you don't. It's called the Pythagorean identity. It's one of the big ones we had. Cosine squared x plus sine squared x equals 1. Or it could be written the other way around. Sine squared x plus cosine squared x equals 1. You see them? They're like the top. They're top right-hand side. Top right. About 4th row down, 3rd row down. You see it? Okay. So this is really just, what, 1 over cosine squared x? Cosine x squared? But that's the same as 1 over cosine x squared. Right? This is the same as this. You square the 1, you get 1. You square the cosine, you get cosine squared. What's 1 over cosine? Secant. So that's secant squared? Which is what you told me when I started the problem, right? Derivative of tangent with secant squared? Well, that's where it comes from. It's just an application of the quotient rule. You can do the same thing for all the others. Like, what's the derivative of cosecant? I'm not going to do it, but if I wanted to, well, maybe I will. What's the derivative of cosecant x? Well, it's negative cosecant x cotangent x, but where does that come from? Well, cosecant is what? 1 over sine? That means I could call u and v Like that, U is the top, V is the bottom, right? This one's going to be interesting. I'm interested to see what you do with this. What would the derivative be? What's the derivative of the top? 0 times the bottom. Careful. Not yet. Times the bottom. Then minus, now the derivative of the bottom, cosine x, times the top. What's the top? Careful. 1, no derivative. All over the bottom squared. Do y'all see this or not? This is u prime v minus v prime u all over u squared. 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 Do y'all see it? The top is just what? Negative cosine, right? Negative cosine x. And then the bottom is what? Sine squared. So how about if I wrote it like this? Since it's sine squared, I could peel off one of them like this. And this is negative. Cosine over sine is the reciprocal of tangent. What's the reciprocal of tangent? Cotangent, and this is cosecant. So this is really negative cosecant cotangent. I mean, I have to change the order, but that's it right there. I don't have to. I'm just saying if I wanted it to follow the formula says a derivative of cosecant x is negative cosecant x cotangent x. But that's the same as this, because it's multiplication. Right, those both mean the same thing? My answer came out looking like this one, but it's the same as this. 2:15. We are going to spend the rest of the day with you practicing, because you can watch me all day, right? You can watch me all day long. You got to get your hands dirty here. But I want to point one thing out that's it's subtle. You okay? Oh, okay. I don't like pointing this out, but I have to, because there are people that will go get help in the tutoring lab, and they'll be giving you help on the product rule, quotient rule, or you'll be asking someone who also is in a different class or something. And I've seen so many people learn product rule and quotient rule, not a different way, but the formula is a little different. So let me first put down on the left side of the page what I told you, okay? I said that if you had u times v, or I should write it this way, I'll do f and g. F times g, I told you that the derivative of that was what? F prime times g plus g prime times f. All right. Then I'll do the quotient to the side here. And then I told you for quotient rule, it was f prime times g again, right, minus g prime times f all over, this case it would be g squared, wouldn't it? That's what I gave you. That's what I think you should learn. That's the way I think you should learn it. If you open up the book to 2.4, product and quotient rule, when they get to product rule, this is what they do. I'm going to put it in black. They do, if you have f times g, and you want the derivative, it's g times f prime plus g times, no. What the hell? No, hold on. Scratch that. It's f times g prime plus g times f prime. That's the way the book has it, all right? Are the answers different? No. They have fg prime. Here's fg prime, right? I have that also. They have gf prime. I have gf prime. I've just switched the order, right? It's plus, so it doesn't matter, right? So you might be saying to yourself, Robert, Mr. D, whatever the hell you want to call me, you might be saying, why you got to be different? Why don't you just follow the book, right? Just stick with the book. Why you got to be different? Because I learned it the way the book did, and it pissed me off. So I'll show you why. I'll show you why. Here's the formula they have for quotient rule. They have GF prime minus FG prime all over G squared. Okay, are our two answers the same here? Well, they have GF prime, I have F prime G. That's exactly the same. It's multiplication, so I can switch the order. Those are the same, right? They have minus, I have minus, right? They have FG prime, I have G prime F. Same thing, over G squared. Yeah? So again, you're asking yourself, why you got to be so different? Why you got to rebel so hardcore like that? Why? Why don't I like the book? Someone tell me why I don't like the book. Let me ask it a different way. When I taught you product rule and then I taught you quotient rule, what's the only difference between the product rule and quotient rule? A minus sign and then divide by G squared. But if you go by the book, they don't even look the same. It's FG prime plus GF prime, and then over here it's GF prime minus FG prime over G. You see what I'm saying? It's almost like two completely different formulas you have to memorize. Does it seem that way? Doesn't that seem like it's two different things you have to learn? Like if you're learning product rule, you have to remember G prime goes first, then F prime goes over here, and then when you learn this one, it's the F prime goes first, then the G prime. Screw all that. Just remember this. Remember that it switches to a minus and it's divided by G squared and you're in business. Right? So when you go to a tutor, wherever, most people are going to do it this way because that's the way they learned it. But it doesn't make a whole lot of sense to me to learn it that way. So, okay? Just be warned. And if I were you, I would tell them, I'm learning it this way, so show it to me this way. And if they're tutoring you, they should be able to adapt to that pretty easily. Maybe they'll go, oh yeah, that works. I like that. Probably not, though. People are set in their ways. All right, you ready to practice? No? Y'all want to just call it a day? All right, we can do that. Y'all had to twist my arm there. So for the homework, this is off page 112. Okay, I'll let you go early, but be ready for a quiz come Monday, okay? First thing we walk in, quiz over power rule, right? Power rule, product and quotient. So if you do your homework, you should be okay. What I would look at here, 3... Are y'all giving me a hard time? I know what y'all are doing. 3 through 23, odd. 23 is interesting. So beware. 23 is an interesting problem. It's got a little bit of, it's a quotient rule problem, 23. It's a quotient rule problem. But the U on top is a product. So you have to do a product rule while you're doing a quotient rule. I want to see how you handle it. Yeah. Okay, I'm going to stop the recording, but I do have one announcement. And